to make sure I can capture any questions you're asking. Okay, so we'll pick up where we left off now that we're finally in. So for the session yesterday, we ended right here talking about the functional groups. And so I mentioned yesterday that we hadn't spoken about the ketone functional group. And so we'll talk about the functional group, and then we'll come back and revisit this question right here. So the functional groups we're going to be studying right now are the kind that contain the carbonyl. So this group right here is called carbonyl. It has a carbon, a double, and an oxygen. And remember, the carbon are bonds, right? So bonded to the oxygen, the other two are bonded to other things. It could be another carbon or a hydrogen, but this group is called carbonyl. So the functional groups we're looking at right now all have a carbonyl group, okay? What we're looking at is, let's see, like I said, this functional group right here. Remember, the oxygen has characteristic bonds, two lone pairs, so it has that right here. You can see how the carbon does have its 4 bonds, right? So this is called the carbon. The carbonyl group itself is not a functional group, but from the carbonyl group, we get the following functional groups. Now, if you look at your textbook, it groups these together. You have this first one here, the second one. So you have aldehyde, ketone, carboxylic acid, and ester. All of these groups have carbonyl groups. So what I'm going to do is I'm going to add a page here, talk about it, and then look at the PowerPoint as though it were a review. We're looking at the carbonyl group right here. Okay, so from this group here, the first group we're going to see, the functional group. So functional groups with carbonyl. Okay, the first one is called aldehyde. So this aldehyde group essentially has the carbonyl in the middle. On one side, it has a hydrogen. On the other side, it has the rest of the molecule. So on the other side is attached to a carbon, and the carbon can be one carbon or many of them, but essentially, when you have this combination attached to another carbon, or just this combination period, the aldehyde. Example of an aldehyde that we are aware of. This aldehyde, I'm going to actually give you the common formaldehyde. If you have taken a biology class, they store all the dead plants and animals in that liquid, and it has a very strong smell, formaldehyde. So at least we are aware of formaldehyde. So formaldehyde is actually the simplest aldehyde. Oh, hold on a second. Sorry. Sorry. So the internet is kind of going out, and I noticed that because of the sign that showed up. If I don't notice it, just let me know. But I saw the sign before you guys said anything. So let me see. Going on. I need to make sure. And you guys can hear me. I do apologize. I know it's hard to have an online. Okay. Okay. Great. So we're dealing with formaldehyde. Formaldehyde actually has the right here having a carbon on the left. It just has. So formaldehyde is a chemical that is to preserve dead things, right? Okay, so once again, in formaldehyde, this combination of atoms is the aldehyde. Okay, so we're going to move on and see other functional groups that have the carbonyl group. The next one is ketone. This is the collective name of that have the following functional groups. Let me add this right here. With ketone, think about common ketones. The most common ketone I can think about is acetone. You notice the same ending in the name. So ketone or acetone here. The carbonyl in the middle. Ketones have the carbonyl in the middle of the compound, not necessarily in the center, on the end. On either side, you have to have a carbon. So a carbonyl in the middle like this, and the carbonyl is attached to a carbon on either side. Oh no. Can y'all hear me? Oh, okay. If you guys can hear me, can you see my screen, the one I'm sharing? Okay, that's, oh, come on. Audio, so three. Okay, I'm sharing my screen. The recording is still taking place. The audio, we're good. Okay, so we're back here on ketones. Once again, we have a carbonyl group in the center. On either side of that carbonyl group, you have a carbon, right? So this carbon can be a really long chain or it can be a short chain, but you have to have the whole combination. So you have to have the carbonyl group and the two carbons on either side. So let me use this to show you what part is the ketone, sorry. And it can be really, really long, right? So this part can have many carbons. It can just be this part here. The example of a ketone here will be acetone that we know as nail polish remover. This is a ketone because it does have that characteristic functional group, right? Which is the combination of atoms that you expect to see. You can see right here in the middle, you have your carbonyl group, and then you have this, and then you have this right here. Don't forget these oxygens have lone pairs right here, okay? So this is acetone, and therefore it's a ketone, okay? When you think about a lot of other drugs that are out there, chemicals, drugs, pills, when they end with ONE, they tend to most likely be ketones. When they end with OL, some drug that has the last suffix OL tends to be an alcohol. If it ends with ANE, it's an alkane. So sometimes the common names of these chemicals retain the systematic name or the name of the family, right? So acetone looks like this. And so we'll go through and cover each of these functional groups later on in the semester. I mean next week, right? Because this semester is not very long. Okay, I'm not done. I forgot. So I've done aldehyde, acetone. Then I'm moving on to carboxylic acid. Our next group is carboxylic acid. With the carboxylic acid, this tends to be essentially organic acids. And with these acids, what we're looking for, once again, is that carbonyl functional group. And to the carbonyl functional group on one side, it can be left or right, you have an OH attached to it. So it looks like a combination, a remix of carbonyl and alcohol. But together, this combo is called a carboxylic acid. So any chemical that has this combination, the carbonyl group and the hydroxide group attached to the carbonyl group, is technically called a carboxylic acid. To the left of the carbonyl group, you may have a carbon, and you can have as many carbon chains as possible. They may be very long or very short. So this right here is the carboxylic acid. I'll talk about a common carboxylic acid. An example of this is called formic acid. So formic acid. With formic acid, you have your carbonyl group right here. You have your hydroxide group on one side. On the left, you have a hydrogen in the place of a carbon. Now you can have a carbon right here or a hydrogen. What identifies this molecule or this compound as a formic acid is the characteristic combination of atoms, carbonyl on one side, either a carbon or hydrogen to the left, and then the hydroxide on the other side. Okay, so this is what you're looking for to identify the carboxylic acid. Where do we know formic acid from? If you've ever been, I'll say, ant bites. If you've ever been bitten by an ant and it was itchy, your skin itches because when ants bite you, they spit formic acid in the wound. And so it burns a little bit and then if it itches for you. Okay, so from your end, it feels like it's itching. From their end, they're trying to spit into the wound to prevent the blood from coagulating or clotting real quick as they do whatever they're trying to do to your skin, right? Ants have goals too. Okay, so we've seen carboxylic acid. Finally, we have number 4. This is called an ester. Ester are essentially salts. I'll say, yeah, they're salts or, yeah, of carboxylic acids. I'll just say derivative is a better word. Derivative of carboxylic acid. It will make more sense when we actually talk about carboxylic acid down the road. Okay, so to get the ester, you essentially start with the carboxylic acid. So we have a carbonyl group here, and then you have the hydroxide like we just had. Then you have the carbon here. I'll make this simple and write this like this. And then what you do here is replace the H from here and put another carbon. Okay, so how do you identify carboxylic acid? Sorry, the derivative, the ester. You're looking at something that looks like a carboxylic acid, right? It has the carbonyl in the middle there. On one side, it has a carbon or hydrogen. On the other side, instead of having a hydroxide, it has an oxygen. In the place of hydrogen, it has a carbon. Okay, so you're looking for this combination. So when I was a student, the way I saw it was I was looking for a sequence of letters, right? So starting with today, what we've learned today, you're looking for a carbonyl attached to a hydrogen to identify aldehyde. You're looking for a carbonyl stuck between two carbons to identify ketone. You're looking for a carbonyl stuck between a hydroxide and a carbon to identify carboxylic acid. Or you're looking for a carbonyl stuck between what looks like an ether, but not really, right? An oxygen and a carbon, and then a carbon on the other side to identify an ester. Okay, so let's go through and see if we can practice this. Oh, I said I was going to review, right? Let's go through this. So this is what we have here. Like I said, the general form, you see how they give you the R here. The R is the rest of the molecule. This R can be either hydrogen or it can be a long chain of carbons, right? But the identifier or the series of series of atoms that tells you this is an aldehyde is your carbonyl attached to your hydrogen, like we see in this example here. Carbonyl attached to a hydrogen on one side makes this an aldehyde. Over here, like we just saw, carbonyl attached to, remember these R's, in this case, they have to be carbons. So carbonyl sandwiched between two carbons is a ketone. And you can see that here in this example of acetone. Even though the hydrogen is written in front of the carbon, the carbon is technically attached to the carbon next to it, and then these hydrogens are technically out here like that. Okay, just in case. Right there, right there, right there. Then this is like that. Dot, 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 dot. Okay, so they show you here in this model that's set up. Okay, so let's keep going. And then over here, carboxylic acid, once again, you have your carbonyl group in the center on one side. So it looks like a combination of carbonyl and alcohol, right? Carbonyl plus alcohol. That's what it looks like, carboxylic acid, at least visually, right? And then down here, remember we talked about COC yesterday being the ether. So here it looks like the carbonyl is right here. And then this combination here looks like, what is it called? An ether, right? So instead of having a hydrogen here, you have a carbon. So let's go through and see if we can actually identify these in problems. There was one more group that I realized they had here I hadn't talked about. That was the amide. Amide right here. So yesterday we talked about the amine, right? Yesterday I mentioned if you have a carbon attached to a nitrogen, and these can be attached to other things. I said yesterday, this is an amine, okay? Now this one here is called an amide, like amide, amide. What's the difference? This carbon here is actually a carbonyl carbon versus just a regular carbon. So you have amide and amine, and these compounds behave very differently. So the good thing is that you guys have access to your notes during the exam and your homework, so you want to make sure you have the right combination of letters and the right nomenclature. So you have carbonyl here, and then you have these right here. Okay, so carbonyl carbon attached to a nitrogen makes amide. A regular carbon attached to a nitrogen makes amine. When I was learning this, I was pacing back and forth because I'm not good at memorizing at all. Even though it appears right now it's been memorized, yeah, the process by which I memorize is very different. So I had to pace back and forth and then write this down over and over again until it stuck. Okay, and every time I saw it, I had a series of steps to help me remember one from the other. Okay, finally, we're getting to practice here. It says identify the functional groups in each compound. Okay, it kind of doesn't help that they have the name here because compounds that end with OL, are usually alcohols, right? But what I'm going to do here, the obvious functional group is this one here. How do I know that? This is your heteroatom. You want to look for double bonds or heteroatoms. So the three things I'm looking for. So when I'm trying to identify functional groups, I do have a process. Number one, I'm looking for heteroatoms. So these are the atoms that are not carbon, not hydrogen. So I located that there and that became my functional group, right? OH is the alcohol functional groups. The second thing I'm looking for is I look around the carbons, right? I know how many hydrogens should be around. If the carbon is on the edges, it should be surrounded by 3 hydrogens. If it's in the middle, it should be surrounded by 2. You see how this only has 1 hydrogen? So I look at hydrogens on carbon. So if I have a scenario like this, CH3, CH2, CH3, I can look at this and say there is no functional group. This is alkane, right? No functional group. Why? Because the number of hydrogens here are what I expect. If you have a carbon on the end, it usually has 3 hydrogens. I said this yesterday, right? The one in the middle has 2. But if they kind of trick me and say CH3, CH, hold on, let me think, CH2, then I'm like, wait a minute, this structure here is tricky. Why? There is a hydrogen here missing and a hydrogen here missing. Usually when there's less hydrogen, that just means there is a multiple bond. Okay? So when you draw your Lewis structure for this part, you have carbon, 3 hydrogens like that for the first one. The second one will have carbon, 1 hydrogen. The last one will have carbon, 2 hydrogens. So the only thing that makes sense here is, of course, this first one has got 4 bonds. This middle one and the third one on the right will have to have 2 bonds for this structure to work. You see what I'm saying? So to accommodate the second bond, they get rid of hydrogens from here and from here. Okay, so just be aware. The easiest way when you're learning this, just draw the lowest structure. That's the easiest way. You go through the long process. When you get the hang of it, if it appears some hydrogens are missing, it's because you do have a multiple bond. So that would be alkene, right? Just in case. So I look for heteroatoms. I look at the hydrogen on the carbon to make sure I have enough. If not, I have a multiple bond. Number 3, what do we do? Heteroatoms. I was really on the road. Now I've forgotten what else I do. I look at that. For right now, we'll go with these two. Yeah, because your functional groups are either heteroatoms or multiple bonds, right? So let me go with that. So for this one here, we can see we have an alcohol here. I might think of the third thing I do. I did say this. If it helps, when in doubt, draw, I should say here, draw Lewis structure, because the Lewis structure shows you everything that's going on, so you can see what's going on. With this one here, though, let me see. I have this. I'm going to give you guys a moment to look at that. So what I'm going to do here is I'm going to erase what I wrote. When you're watching the video, feel free to rewind. I'm glad the internet is not cutting out now, so at least the video can be smooth from here on. Okay, so for this one here, I have a nitrogen, a carbon, a carbon, a carbon, a carbon, and nitrogen. So I have 1, 2, 3, 4, 5, 6 central atom. Nitrogen, carbon, 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 and then nitrogen. Do I have 4 carbons? Yeah. So nitrogen on the left is attached to 2 hydrogens. That's these right here. It's also attached to the carbon in the middle. The carbon has 4 bonds. All the carbons have 4 bonds, I'm assuming, until I know otherwise. Nitrogen has got 2 hydrogens like that. The normal bonding pattern for nitrogen is 2 dots right here, 2 dots right here, and then 3 bonds, right? For hydrogen, I have 2, so this is done, up and down, that, up and down, done. Okay? So now that I'm looking at this, I can see, wait a minute. I'm either dealing with amine, right? Or amide. So which is which? Remember, when you have the carbonyl carbon, that's the amide, the one that has the oxygen in it. If you just have a carbon and nitrogen, this is double amine. Amine here, amine here. Okay? So this is going to be amine. Okay. So with this one here, actually, they kind of made it easy for you. You don't really have to draw the structure. This right here will be a phenol or benzene. Not phenol, sorry, that's not phenol. Phenol has hydroxide. It will be a benzene or phenol. Like either this phenol or benzene. Okay, and then you have a double bond here. That will be your alkene. Okay, so this styrene has got 2 functional groups, and you want to be aware of that. At any point, if you guys have questions, please feel free to ask. Okay, so with this one here, as I'm looking at this, I do recognize that I suspect CHO is one of the ways in which they write the aldehyde. So let me go ahead. I'm going to need some more space for this part here. So I'll just copy this part and paste in the bottom. Copy and paste here. Oh, come on, paste. Okay, so for this one, please note that CHO is another way of writing carbonyl and hydrogen. I told you chemists are lazy, right? So many times if they don't want to do something, they're like, okay, we're going to come up with a short way. Everybody adapt, and then they go from there. So this is another way of writing that combination. So if you see CHO, you want to think aldehyde. Okay, so based on that, you can rewrite the structure as a carbon O and a hydrogen like that. Okay, so what if this was an alcohol? Because that would be my question. I thought alcohol was OH. What if I thought this was an alcohol? If it was an alcohol, they will write it like this. Okay, if this was an alcohol that had a carbon right here, the alcohol will look like this. Okay, so this will be written like this. Condensed, right? It'll be written like this, CH2OH. Okay, so with the alcohol, they write it as OH. With the aldehyde, they write it as CHO. So when I was in school, I was like, CHO aldehyde. Like, what is she saying? I was trying to memorize this. CHO aldehyde. If they write it as COH, co alcohol. Okay, so alcohol, and this is aldehyde. Those small things. Plus, with the alcohol, you have these two extra hydrogens because there's no double bonds. Okay. Okay, what else was I working on? That was the first one. Oh, yeah. Second one, we have, it looks like a carbonyl. How do I know it's a carbonyl? If you look at the structure, you have the carbonyl right here. On one side, you have a carbon. On the other side, you have a carbon. So when you have this and then you have carbons on either side, this is called a ketone. Okay? Because the ketone has this combination right here. Carbonyl in the middle, carbon on either side. That's called a ketone. Okay? Acetone. I've seen a lot of steroid medication that have a lot of "one" in them, and I'm like, yeah. I have mixed feelings towards ketone products, even though I do like acetone. This one here, you can see right here. Let me see if I can draw it out. Now just copy it over. But you can hopefully begin to see, right? This is an amide because it has that carbonyl attached to a carbon. Let me see, can I copy that? It's disappearing. You find your carbonyl if possible. Come on. There. Okay. Find your carbonyl. Oh no. Sorry guys. I don't know why this is not working right. I did copy it over and over again. Okay. Copy. And then it pasted the wrong thing. Paste. Okay, finally. So I do have my 5-membered ring here. Carbonyl right here, right? Y'all see it. So the carbonyl is attached to a carbon on one side. What's on the other side though? On the other side is directly attached to the first element we see right here, which is the nitrogen. So when you have this combination of carbon attached to a nitrogen, but carbon is also attached to an oxygen via double bond, this is called an amide. Amide, like that. Okay? So we're making progress. And then we'll finish with the talking about Tamiflu, the medication. Let's see. Do y'all have any questions? If you do have questions, feel free to type this in the message box because then I can address them accordingly. Let me copy these two. I think I can copy them both at the same time. Put them right here. Paste image. Okay. We're doing a little better. Okay, so with this one here, once again, they're writing shorthand, right? That laziness thing. But we have to be able to understand what they're writing and how they write it. So, of course, the rest of this has the right number of carbons and hydrogen. This is right. We have to decode what this is. When they write CO2, it looks like carbon dioxide, right? So CO2, this is essentially CH3, CH2, CH2, COOH. But how do you actually draw that in the Lewis structure? Remember, the context here is it has a carbonyl. So these two elements will be used to make the carbonyl group, and then the OH will be attached to it. So we have CH3. I'll leave this in the condensed form. And then for this part here, I'll write it like this. C double bond O, right? To the right of that, I'll put OH. So remember we said when you have a carbonyl in the middle, to one side you have it attached to a carbon, to the other side it's attached to an alcohol. This is called carboxylic acid. Okay? So the important thing here is to remember when you notice the carbonyl, what is it attached to? So this is a carboxylic acid. We finally have this here, and this time, this looks a lot like this one up here. The difference though is instead of having a hydrogen on this end, we have a carbon chain. This is called a carbon chain. So I have CH3 over here on the left, CH2, right number of carbons and hydrogen. Then in the middle here, when I have COO, I used to call it cool. I did silly things to remember this, right? When I have the COOH, I know it's carboxylic acid. If it's COO but C, cook, then that's an ester, okay? So if it's spelled cook or, yeah, cook, it's an ester. COOC. So with that here, the C and the O become the carbonyl. To its left, we have the CH2, CH3. To its right, you have an oxygen and then CH2, CH3, and this is called the ester. So weirdly enough, ester compounds have beautiful, pleasant smells. And if you when they make esters, they use them as flavoring agents for gum, different drinks. Sadly, we're not on campus, but if we were on campus, we'll make esters in the lab and then you get a chance to smell them. Okay? So I think it's ironic that the chemical that has a beautiful smell, beautiful and pleasant smell, is called an ester. The one that has a strange smell, the benzene ring, is called aromatic. I think that's strange, right? But yeah. So when I was learning this, I was like, oh, Esther, like a girl's name. Imagine Esther, the girl, is wearing beautiful smelling perfume. And that's the logic I used to memorize this. I know it probably doesn't make sense. It helped me remember this because I was learning it very fast too. Okay. And I'm not the best memorizer at all. Okay. We're working with Tamiflu, an antiviral drug effective against avian influenza. Identify all the functional groups in Tamiflu. Okay, let me zoom this in and see what we have here. So, do you all see any functional group you want to point out to me? I see a couple. Okay. Do y'all see any functional group here? I'm going to highlight them with the highlighter. Okay, you want to tell me which one? And all of these functional groups, okay, the carbonyl, very good. All of these functional groups have chemical reactions, right? So when I look at Tamiflu like this, I'm like, okay, I see why it works, but I also see why it has these crazy side effects, right? They tell you what it does, and when it does, it's like a one-liner. It helps you with the cold. Maybe they have extra stuff. It helps you with decongestant. Maybe it has extra stuff. It helps you with a headache. And then side effects. There's a whole paragraph, right? Because I usually think functional group, all those functional groups are in there reacting. These functional groups are the site where the reaction takes place. So you mentioned carbonyl, right? But the carbonyl has a nitrogen, right? So this is going to be called amide. If it had a carbon on either side, it would be called ketone, right? So we're looking at this combo here, and we're calling that amide. Okay, what else? Does anybody see another one? It's kind of like a puzzle once again, right? So look for your heteroatom or your multiple bonds, and then you want to look around it and see what series of atoms do we have, and then what combination do you think we have. See, at least I see three other heteroatoms, right? The oxygens and the nitrogen. So let me go for the oxygen. That's the easier one. This oxygen here. Okay, it's not double bonded. The bonds are apart, not together, right? So the scenario where I know oxygen in the middle surrounded by two single bonds is either alcohol like this or ether like this. So let me look at this. Do I have a hydrogen on one side here? No. So I don't have an alcohol. This would be alcohol if I had alcohol. This is actually an ether, right? It's COC, ether, versus COOC, ester. I know. Yeah. Yeah, I was walking around saying this to myself, okay? And I know I look special. It was the process. So we see the COC here, and so that tells us this is the ether. And they do well to try to show it to you guys by kind of displaying it, not really highlighting it, but displaying it. Okay. And then let me see. I see another heteroatom nitrogen. I see this right here. Okay. So I'm thinking of all the functional groups I know that have nitrogen in them. I know one where the carbon is attached to a nitrogen, right? And then they have their bonds. And this is called amine. And then the other one has a carbon attached to an oxygen attached to a nitrogen. And this is called amide. So there was this guy who was selling, he wasn't really selling. Right, right. So this would be Amin. He was kind of, he's a financial advisor, and then he came to speak to me. He's like, "Hi, my name is Amin," and he kept talking. And I'm like, I have this big smile on my face, and he's thinking I'm gonna, buy his product. And when he gets done, I'm like, "Oh my goodness, do you know what your name means?" He's like, "Yeah, I know. It's a molecule in chemistry. Are you gonna buy stuff or not?" I'm like, no, I don't have money right now, but this is so cool." And he just looks at me like, "Oh, you're such a nerd," and he walked away. I work with him now though, so when I finally did get money, I called him back. I'm like, "I want to work with you because your name is Amin." He's a good worker too, so that helps. Amin, exactly. Because you got a carbon attached to a nitrogen, right? And this carbon is not directly attached to an oxygen. So this is Amin. Very good, guys. It does take a little bit of training to figure this out. Okay. I see the double bond. I'll get to that. This one here shows that we have two O's and then C and then H and then the rest of the molecule. So remember I said earlier when you have two O's and C, cook, cooch, like that, you can say this is ester. And remember ester has the carbonyl, on one side a carbon, on the other side an oxygen, then a carbon, right? It can be written out this way or it can be written out this way. But this would be an ester, the one that smells nice. Then finally, we have double bonds here, so that will be the alkene. So imagine this one compound has all of these functional groups. Which is the most dominant one? We don't know. One of the ways to tell the dominant one is to look at this is the common name, the trade name. The trade name. You want to look at the systematic name that's based on the chemicals present, and then the last suffix will tell you which is the most dominant group. Okay. Okay, so we're done with that part. Let me see. How am I doing? Oh, let me go over this part real quick. I'll just show you. See a nitrogen here. There's no oxygen nearby, so that will be amine. This one here has an oxygen. There's no double bond, so that will be an alcohol. And look at the name, atenolol. So it ends with OL. So most likely the alcohol here is a dominant group. I see an oxygen. On one side I see a carbon. On the other side I see a carbon. This would be an ester. I see this whole ring here. This is going to be a benzene ring. And then we have the carbonyl here. On one side we have a nitrogen. Carbonyl and nitrogen combo is amide with a D. Is this the one that has, yeah. This is for high blood pressure, this medication. You can see why it has a lot of side effects, right? And then mestranol is synthetic contraceptives, birth control pills, right there. See when it has the word OL in it, it has the alcohol. So when I see OL, I'm looking for alcohol. There's our alcohol. Carbon, COH, right? Alcohol. triple bond, alkyne. And then we see that ring again, benzene ring. These things have a lot of chemicals in them, right? That's why they have all those strange side effects. So let me see. For this one here, I see the oxygen. To one side, I see a carbon. Because remember, the hydrogen is never in the middle. So the hydrogen, even if it's drawn here, is always bonded to the end. So technically, the carbon is bonded to the oxygen, not the, yeah, the oxygen is to the right of the carbon and the hydrogen is to the left. So on one side, it's a carbon. On the other side, it's bonded to a carbon. So this makes it an ether. I had to think for a moment there. Ester is COOC. Ether is COC, right? Okay, so we're finally getting to the alkanes. And I know you guys have, some of you have worked on this lab because I was trying to grade it earlier today. Alkanes, as we have seen, these are hydrocarbons, meaning the compound is made of only carbons and hydrogen. The carbons all have single bonds. The carbon and hydrogen has single bonds, okay? We saw that there are two forms. You have the acyclic form of alkane where there are no rings, or you have the cyclic form. The acyclic form, when they give you the molecular formula, it has to match this order. It has to match this formula right here. So say, for example, I'm trying to write a formula where there's only one carbon, okay? I'm trying to write an alkane formula with one carbon. That means N must equal 1. For that, I'll say C1H 2 times 1 plus 2. So this ends up being C. In chemistry, the sub 1 is assumed, so you don't write it down. And then this is H. And then 2 times 1 is 2 plus 2, 4. So CH4 is essentially the simplest alkane we have. And this is called methane. Okay? So when we're drawing alkanes or we're writing the formula out, we have to remember the number of hydrogens and carbon must fit this formula. All alkanes fit this formula right here. Okay, and this is true for all acyclic alkanes, the ones that are not cyclic, the ones where the first element doesn't attach to the last element. Okay, so these are called acyclic alkanes, and they're called saturated alkanes. When I was a student, I tend to obsess with words, so I was like, what do you mean saturated? Like water saturates something? And I realized, since you guys have worked on your lab, we do have 3 different hydrocarbons, right? The alkane, let me write on a new page. I tend to be lazy and write on the same page. Let me add a new page. So what does saturated mean? Saturated just means maximum amount of whatever, okay? So in our context, we're saying alkanes are saturated. So what do we mean by that? Let's look at the general formula and we'll see that. Alkanes essentially have that general formula that says CnH2n plus 2. Okay? Alkenes are very similar to alkanes, but alkenes have 2 less hydrogen. They're CnH2n, and then that's it. And then alkynes have 2 less hydrogens. I'm going to write here 2 less hydrogens. Then alkynes also have 2 less hydrogens. So with alkynes, the general formula is CnH2n minus 2. So these have 2 less hydrogens than alkenes. If you compare alkynes to alkanes, they have 4 less hydrogens. Okay, so if you're comparing these 3 groups, which ones have the most number of hydrogen? Alkanes. For that reason, alkanes are called saturated because they have the most number of hydrogen possible for the carbon. Possible. Okay? Because at first I was like, I am not good at memorizing, but if a word makes sense in the way it's being used, then I can easily recall that word. Well, I cannot guarantee the easily part, but I will at least work on recalling the word. Okay, so alkanes are saturated because they have the most number of hydrogens possible, while alkene have two less, alkyne have even two less, right? So all alkanes have to fit this general formula. Alkenes have to fit the general formula. Then finally we have alkynes that have to fit the general formula. Okay, so yeah, maximum number of hydrogen atoms per carbon atom. Okay, I'm trying to go in order. Now, we have acyclic alkanes, the ones that look like a strand of pearls that's not chained up. And then we have cycloalkanes. These are the ones where the carbon atoms in the beginning and the end are joined together to make a ring. We discussed this yesterday. Because you have to, let me pick one that has 3 carbons. I'm going to draw an acyclic alkane, right, to explain this. And then compare this with a cyclic alkane so you can see what's happening. With an acyclic alkane, please notice that you have 3 carbons in series, back to back to back, and they're attached to the maximum number of hydrogens possible. Each carbon has to have 4 bonds, as you can see. 4 bonds, 4 bonds, 4 bonds. There. Now I want to make a cyclic alkane from that. In the cyclic alkane, the carbons are the ones connected to each other. So the first one has to connect to the last one. So I'm going to write a carbon on the right, one on the left, and then one on the top. And these have to attach to each other, right? So in doing so, now each carbon has got 2 bonds, and they're just missing 2 bonds. So a bond here, 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 a bond here. So when I itemize what I have, I look at my carbons. 1, 2, 3. I have 3 carbons, right? I look at my hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 hydrogens. So this formula will be C3H8. Okay. What about over here, my cyclic alkane? C3, right? 1, 2, 3. And then H's. 1, 2, 3, 4, 5, 6. H6. So in order for me to go from the acyclic alkane to cyclic alkane, I actually had to take off this hydrogen and then connect this end to that end to make this. In the process, I lost 2 hydrogens. Okay? So cycloalkanes tend to have 2 less hydrogens. For that reason, they have a general formula, and this matches the alkene, right? Because to connect the free ends of carbon, you have to get rid of 2 hydrogens. So they have the same formula like the alkenes, okay? Okay, when you're looking at a chemical's name, if the suffix, kind of like its last name, ends with ane, most likely it's an alkane. Okay? If it ends with ene, alkene. If it ends with yne, alkyne, right? Then we have all the other ones. So here we're asked, how many hydrogen atoms are present in each compound? Oh, okay, this looks fun. I like puzzles. So for me, yeah, I went from hating organic to loving because I realized that I could look at it as a puzzle, like one of those games where, you have to figure out, solve mysteries and stuff. So I was like, I can do this. Okay, so this is the condition. We have to have an acyclic, so that's a straight chain, alkane with 3 carbons. Okay, if it's an acyclic alkane, the general formula is CnH2n plus 2. If the carbons are 3, that means N is equal to 3, right? So this is going to be C3. 3 times 2 is 6 plus 2, 8. H8. Do they want the formula for me to draw it? Oh, they're asking how many hydrogen atoms are present. I guess 8 hydrogen atoms? Oh, right here, 8 hydrogens. Next one, a cycloalkane with 4 carbons. Okay, let me see if I can do this. Come on. Okay, cycloalkane with 4 carbons. So cycloalkane. The formula for cycloalkane is CnH2n. Remember, to make the cyclo part, you have to drop 2 hydrogens. So this is all we have. If it has 4 carbons, N is 4, right? So C4H 2 times 4, 8. Huh, interesting. 8. Now I'm wondering, do all of these have 8? No. We'll see. I don't want to get ahead of myself. Okay, copy. And let's see this right here. Okay. Cycloalkane, again, CnH2n with 9 carbons. Okay, so N is equal to 9, right? C9, 2 times 9 is 18, H18. Okay, finally, breaking it up. 18. And then an acyclic alkane with 7 carbons. Oh, that wasn't that bad. I didn't have to do all of them. So they want 7 carbons, acyclic. I'll start skipping through some of these questions so we can actually make progress in this, because I feel like as I'm adding pages, it's adding more pages here. So acyclic alkane, CnH2n plus 2 with 7 carbons. So C7, 7 times 2 is what? 14 plus 2 is 16? H16. I'm not very good at those basic head math stuff. Let me see. I think this is correct, right? 14 plus 2. Okay. Oh, so here. Thank you. Which formula represents acyclic alkanes? So the one that's cyclic is CnH2n, right? Acyclic is CnH2n plus 2. So the one where the second number is double the first number is cyclic. So let me go through and figure that out. For number 2, 8 is double of 4. So this is cyclic. 24 is double of 12. So that's cyclic. See how I'm going through this real fast now? Okay. So these other two are not cyclic. So this is going to be, of course, if it's cyclic, it's going to be cycloalkane, to answer the question. Cycloalkane. Okay. So this one here, I want to verify. You want to double the first number and add 2. So if I double 5, I get 10. I add 2, 12. Yeah, so this is just regular acyclic alkane. Take 10, double it, you get 20. Plus 2, 22. Acyclic alkane. Okay? Yeah, not that bad. Okay. So you guys haven't had a chance, we're now getting to naming nomenclature. You've had a chance to draw the Lewis structures. I want to make sure that at least you're covering something in the beginning before we got here. So we're now going to be dealing with prefixes. Organic names tend to be like charades in a sense that it may not be as fun as charades, but it's descriptive. It's not just a name. The systematic names, so I'm going to say here, systematic names are descriptive. Descriptive. Okay. Is it DE? Yeah, DE. Okay. Yeah, my spelling is not the best. Okay, so the prefix here, meth, is a prefix. This is a prefix that stands for 1 carbon. And then ane is a suffix, that's kind of like a last name, that stands for alkane family. So it'd be kind of like your last name, right? So meth is just 1 carbon, and then ane is alkane family. So when you say methane, this gas is methane. We smell methane. What you're saying is we smell a chemical compound that has 1 carbon in it that's in the family of alkanes. Okay, so you can see right here, this is what the structure formula looks like. Bond angle 109.5 because you have a tetrahedral. You guys had a chance to go over that in your lab, right? When you have a structure of the molecule, this is a 3D structure where it looks like, so because I'm not great at memorizing, I'm always relating what I learned to things I know or my experience. Okay, to be honest with you, I did say this is like a chicken foot. Okay, when I was learning this as a student, being African, I'm like, tetrahedral is giving me chicken foot vibes. Okay, and yeah, but since I'm not back at home, I'm here. I would say a tripod stand. Okay. It doesn't have as much sentiment to me like a chicken foot because I'm like, yeah, I've been seeing them chicken feet, and it looks this is what I'm thinking of when I see that tetrahedral. So anytime I see that anywhere, I'm like tetrahedral because it reminds me of that experience I've had in life, right? And this is how I remember. I don't remember like other people remember. It's always this relates to that, right? The bond angle, because it's not flat, really, like Lewis suggested, is 109.5. Okay. So then they go through all here and give you the different names and the structural formula based on the number of carbons. So please note, I'm going to highlight this here. The ane part just says they're all in the same family of alkane, right? All the ane and the ane and the ane. They're all alkane, meaning that they all have single bonds, right? And maximum number of hydrogen. Now we want to focus on the prefix. Mes means one carbon. See, one carbon, one carbon. S means two carbons. Two carbons here, two carbons here. And in the picture also two carbons, one carbon. Prop means three carbons. If you think about isopropyl alcohol, that prop part is just telling you that alcohol has three carbons. Okay. Bute, this is bute. Bute is four carbons. I'm trying to think about, do we use butane here? Sometimes butane for gas. I'm trying to think about anywhere else where we use butane. I can't think about it right now. If you can think about it, please share. But yeah, butane, four carbons. Pentane, five carbons. So mes, s, prop, bute, pent. Do y'all have any questions? Because I can just go on and I can just ramble on. Okay. So while we're here, y'all don't ask a lot of questions, that's fine. While we're here, I'm the kind of person that has an active imagination. I'm like, I've heard of the word mess a lot in other contexts, on TV, in movies. Yeah, SVU, things like that. Does that compound have one carbon? Yes. Mess stands for one carbon, right? There are other things in it, but yeah, at least it has that part there. Okay, so moving on. So ethane, we can see here two carbons. They show you the structure here. You guys have a chance to go over that. So I want to spend a lot of time here in the details of the structure. Realize that this is the Lewis structure. Lewis is a scientist whose idea of the chemical structure was very simplified. He felt like the bonds were all vertically lined or horizontally lined. Very neat, very OCD. In real life, this is the Vesper. The Vesper model or the 3D model. These are what the actual molecules look like. They're not 3D like Lewis. Lewis is a good structure to start off when you're trying to draw it to see what connects to what. But when it comes to the spatial arrangement, this is what they really look like right here. Same thing with this prop. You have three carbons in series, and this is what they look like. So when you're trying to draw your 3D representation, just in case you're working on the lab, the easiest way to draw this is the carbons tend to arrange themselves in zigzag. Okay, so I draw them first. Sometimes I even just draw a zigzag line, like a chevron, like that zigzag. Then I put in my carbons. Then I fill in the rest of the molecule, whatever comes in there. But the carbons in the middle, the central atoms, they tend to have that zigzag chevron connection. Okay, so notice that here, right? And the longer it gets, the more zigzaggy. I don't know if that's the thing. It gets. So once again, we have Lewis here. We have the 3D. Okay. Oh, we talked about this yesterday when we're talking about isomers. So we're told here, this molecule is exactly like this molecule because technically these carbons are in a row, right? These are in the same row, and this one is bent. But think about it this way. As I was trying to make sense of organic chemistry, I came up with a lot of very imaginative stories. Imagine if you're trying to describe this, right? Let's label this carbon 1, and this is carbon 1, carbon 2, carbon 3, okay? So you're saying, oh, I have an alkane, a chemical compound, where there's three carbons arranged in series back to back. The one on the furthest left is carbon 1, followed by carbon 2, then carbon 3. So carbon 2 is between carbon 1 and 3. Okay, I got it. Then I have another one over here, carbon 1, carbon 2, carbon 3, where essentially it's the same scenario. Carbon 1 is before carbon 2, they're directly connected. Carbon 2 connects to carbon 3. So carbon 2 is essentially between carbon 1 and carbon 3, right? Even though this visually looks bent, it is not bent. Even though it appears bent, we don't really consider this bent, right? Because remember how we have that bent molecule with water like that? That would kind of confuse you. Let's call it branched. Branched is a better term. Even though this one looks branched, it's technically the same as the left molecule. Why? Because carbon 2 is still between carbon 1 and carbon 3. It's just branched. Okay, so branching a molecule does not create a new molecule, just creates a branched version of the original molecule. So hopefully you guys see that, right? If you're trying to make something completely different, you need to have at least 4 carbons to make an isomer. Okay, so here they had the isomers, and we worked on this yesterday, right? Where we had 4 carbons in series. We broke off one end and attached it to the middle right here to get something like that. And then this is a condensed form. We saw this yesterday. Okay, so we covered this yesterday and we're covering it again. Butane and isobutane are isomers of each other. What is an isomer? An isomer is a term used to describe two different compounds that have essentially the same ingredients or the same molecular formula. So when you're looking at these two compounds, I remember Elizabeth asked me this yesterday. So you're saying if two compounds are isomers, they have to have the same molecular formula. Yes. So the molecular formula on the left of butane, let me see, it has 1, 2, 3, 4. I have 4 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I have 10 oops, no, not like that. 10 hydrogens, right? Over here on the right, my molecular formula has how many carbons? 1, 2, 3, 4. I have 4 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. So wait, in order for butane and isobutane to be considered as isomers, they have to essentially have the same molecular formula. What makes them different? The atoms are connected differently, especially the central atoms. They're connected differently, so the chemical comes out behaving differently. So when I was trying to relate this to my life again, I am such a selfish learner. That's not really a category of learning, but that's what I call it. Where even though this subject is about carbon, somehow I have to be involved in the process, right? So I'm like, let me see. What do I know in life, my life, that reminds me of this scenario? You want to know what I thought about? Siblings. Like when siblings, not twins, just siblings, brother, sister, whatever, they're related, they come from the same parents. So the molecular formula essentially would be like the parents, or maybe the same genes, whatever, the parents, and then the kids look kind of different. So butane is from that molecular formula, and so is isobutane, but their behaviors will be very different because the arrangement of the atoms came out differently. So you have siblings, right, from the same parents, and you're like, how are we even related? When you're fighting with your sibling, how are we even related? You must have been adopted. You shouldn't say that. But yeah, because we're so different, but we came from the same parents, right? They have the same molecular formula, but their behaviors are very different. Okay. Yes. They have different physical properties too, depending on how different they are. Because you see, spatially, They have different physical properties, different chemical properties too. So what makes you know they are isomers is the fact that, quote unquote, their chemical formula or molecular formula is the same. Okay. So we'll talk about different isomers because I think your lab, I don't know if it's a lab for today, one of the labs, I get confused now, has you separating two different formulas based on whether they're different completely or spatial isomers or constitutional isomers. So essentially, we said these are isomers, right? The proper term to describe this is the term constitutional isomer. So constitutional isomer. We know for sure they have the same molecular formula, so they have the same molecular formula we checked, but different arrangements. And many times with these, the name will be different too. It will be a more obvious difference. So we'll look at scenarios where the names are very, very similar, right? Okay, so let's look down here. So we're told, right, isomers is used to describe two different compounds with the same molecular formula. Constitutional isomers, these are molecules where they differ in the way the atoms are connected to each other. We just saw that, right? So now we're kind of detouring a little bit and looking at constitutional isomers where they are not hydrocarbon because you have a heteroatom here. So let me see. I have to do a quick check here. What's the molecular formula on the left? How many carbons do I have? 1, 2, 2. How many hydrogens? 1, 2, 3, 4, 5, 6. H6. How many oxygens? 1. O. The one on the right. How many carbons do I have? 1, 2, 2. How many hydrogens do I have? 1, 2, 3, 4, 5, 6. 6. How many oxygens? 1. Okay, so these are isomers. But look at how they're connected so differently. They're connected so different. They have different functional groups. Okay, so if I erase all these markings on here, on the alcohol side, you can see the oxygen is as far right or far out as it can be. On the ether side, the oxygen is in the middle. So for me, visually, what I see here is CCO, right? And then here I see COC for my central atoms. I'm talking about this arrangement here. CCO, COC. The bottom line is these are constitutional isomers because the molecular formula is the same, but they even have different, they definitely will have different names. They'll have different behaviors. Well, this alcohol is drank. This one here is not drank, not for drinking. This is an ether. Has very different behavior from the alcohol, right? Very different behavior.
I actually have a question, if that's okay.
Yeah, that's okay.
It has to do with the lab, but it has to do with ethanol on question number
Okay.
5.
Okay.
It was asking about hydrogen bonds. Does, if you go back up a little bit, yeah. So the formula that it shows is for dimethyl ether, but since its isomer has the oxygen hydrogen bond, does that mean that it's possible that it has a hydrogen bond?
Okay. So with the hydrogen bond, there has to be a direct connection. So let me erase all this stuff here, all the scribbles. With a hydrogen bond, you have to have O directly attached to H. They can't just be in the same formula, they have to be directly attached. And then or N directly attached to H and then F to H, right? So that's what we're looking for in a Lewis structure. You have an O here, but it's attached to a C, and the same thing on the left. So left and right, the O is attached to a C, and all the H's are not directly attached to an O, so this one here has no hydrogen bond at all.
Okay.
Okay, this one here, you have an O on the right attached to an H, so this one has one hydrogen bonding site.
Okay.
There has to be a direct connection, right? Does that answer your question?
Yes.
Yeah. So if this has a hydrogen bond, then you know it also has dipole and then London dispersion force. This one has no hydrogen bond, but because it has a heteroatom and none carbon, none hydrogen, so it's at least going to be dipole and LDF. Does that make sense?
Yeah, that does. Thank you.
Okay, you're welcome. So to kind of review what we did yesterday, they actually make isomers of pentane. So you have regular. So they call this regular pentane, the non-exciting pentane, normal pentane, implying the other ones aren't normal. But anyway, so pentane, pent is 5 carbons. So you write the 5 carbons in series for the regular pentane. And then to get this one here where you have 1, 2, 3, 4 in series, break off one of the edge ones and put it, you can't break it off and put it right here because you're right back where you started. You want to break it off and put it in one of the middle ones. So you break this off and make sure that the piece that broke off, the CH3, is not attached. Once it breaks off, this will now become carbon 1, carbon 2, carbon 3, carbon 4. So before you break the corner piece off, this is carbon 1, 2, 3, 4, 5. If you plan to break it off, break the corner piece off and attach it to either carbon 2, 3, or 4, not the end pieces, because you're kind of starting back where you left off, right? So when you attach it, oh, sorry, I said it wrong. This is 1, 2, 3, 4, 5, right? When you break this off, then the numbering changes. So this becomes 1, 2, 3, 4. Attach it to the middle pieces so it can be the 2 or 3. So when this breaks off, you see how they place it on the new carbon 2? This is now carbon 1, this is 2, this is 3, this is 4. And that makes an isomer. Then you break off another piece. In this case, break up the piece on the right here. When you break up this piece on the right, this is now 1, 2, 3. You always want to attach the broken off piece to the middle piece. So the broken off piece goes to carbon 2. And that's how we get this last isomer right here. Okay, I know I went over this yesterday, but I wanted to make sure we went over it again. Okay, so they go through here telling you the remaining prefixes. Hex stands for 6, so we have hexane, heptane, octane, nonane, decane. So dec for 10, like in a decade. Nonane for 9, octane for 8, and then heptane for 7, hexane for 6. So okay, so here's the questions, like your lab work, right? Are the compounds in each pair constitutional isomers or are they not isomers of each other? First thing you want to do, itemize and find your molecular formula. Molecular formula. Carbon, 1, 2, 3, 3. Hydrogen, 3 plus 2 plus 3. What is that? 8? C3H8. Okay? This one here, 1, 2, 3 carbons, C3. Okay. 1, 2, 3 plus 3, 6, H6. Okay. The molecular formulas don't match. So these are different compounds completely. As in not isomers. They're not isomers at all. Okay? Because they didn't meet the first prerequisite. What about these ones here? 1, 2, 3. C3. N. 1N. 3 plus 2 plus 2 plus 2. H9? I should write it differently. That looks like a weird form of C3H9N. 3 plus 2 plus 2 plus 2 is 9, right? Okay. I get stumped with things like counting. Okay, what about here? Carbon. 1, 2, 3. 3. Hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9. H9. Nitrogen. 1. Oh, look at that. But they're connected differently, right? So these are constitutional isomers. Oh, there's more here. How much more is there? Okay, that's fine. Finally, we're getting to IUPAC naming. Okay, are the compounds in each pair isomers or are they not isomers of each other? Same thing here. I'll skip over the first one. I think it's pretty clear. I'll do the second and the third. First one, 1, 2, 3, 4, 5, 6. I'm counting the carbons. Remember, each corner where the lines meet is a carbon. So I have 6 carbons. And this has no double bond. That means we have the maximum number of hydrogens possible. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. Okay? This one here, I have a carbon here, a carbon here, a carbon here, 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 here. C6, 1, 2, 3, 4, 5, 6. Yeah, C6. Then I want to bring in the hydrogens. I have a hydrogen here. There's a hydrogen missing here to give that carbon 4. 1, 2, 1, 2, 1, 2, 1, 2. Okay, for the hydrogens. Let's see. There's 3 here. 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. Huh, look at that. They're definitely isomers because their formulas, the molecular formulas matches, but they look different. So these are constitutional constitutional isomers. What about this one? Same thing. 1, 2, 3 carbon, C3. Hydrogens, 3 plus 2 plus 2, that's 7, right? 8. I stumble with the counting part. 8, and then this is 0. So 3 plus, yeah, 8, 0. Okay. 1, 2, 3 carbons, so C3. And then 3 plus 2 plus 3, that's going to be 8. So H8, and then 1 O. Yep. Different functional groups, but they have the same molecular formula. So these are also constitutional isomers. Okay. Okay. So with the IUPAC system, this is the technical name for the chemical, and it's recognized internationally. Okay. So I'm going to go straight to the naming part. With the name, each alkane name has 3 parts. The parent name. So essentially, when we're looking at a name of the alkane, like if we're looking at a name of a person, usually a person may have 2 names or more, depending on where they're from. Their culture may influence their name. When it comes to alkane, the longest chain, the longest continuous chain, influences what we call the parent name. So we're told here the parent name indicates the number of carbons in the longest continuous chain in the molecule. So you have the parent name, and then you have the suffix, the part that comes after the name, and the suffix indicates what functional group is present. So suffix goes with functional group. The parent name has to do with the number of carbons. For example, meth, S, prop, bute. This one here is number of carbons. And then we have a prefix. The prefix part of the name, this identifies the location and the carbon number of any side groups we may have. So this is the side groups. Okay, so let me give you guys a visual real quick before we start nomenclature. So when it comes to organic compounds, sometimes organic compounds are as simple like this. Okay, with 5 carbons in series with the right number of hydrogens. Sometimes they're that simple, straightforward acyclic chain, not branch. Okay, but sometimes we have side groups on the longest chain. So for this one here, I'm going to show you this combination here, CH3, where these 2 groups are put, one is put on the top and the other one is put on the bottom right here. Actually, this H doesn't belong there because now this has too many bonds right there, like that. Okay, so here we had 5 carbons for the longest chain, right? The longest continuous chain, like back to back to back. If you were to line them up, how many carbons do you get back to back? we have 5 carbons. If you are to look at the central carbons, the ones in the middle, how many are lined up back to back? These are 3 carbons. And then the 2 remaining carbons look like leaves coming from a branch. So this one here looks like a branch, and then the ones on the side look like leaves coming from the branch, right? So these are essentially your side groups. These are named first. The length of the chain is named second, and then the family of the chemical is named last. Okay? So the idea of how we name it is such that when we are done, we can reproduce the molecule from the name. That's what I was talking about charades. Okay? So here we're being told the side groups or the leaves in the picture I just drew are called alkyl groups. And for them, instead of using the word, let's say methane, you use the same prefixes, but it ends with Y. So this would be methyl. Okay? So methyl, ethyl, propyl, butyl. The YL we're using all the time indicates to the person reading, this is not, this is one of those branches. This is one of those side groups. The leaves on the, I guess, branch, right? This is more like a leaves of the side group. Okay? So as we're going through this, it will make more sense as I'm working on this. So I'm going to skip over this part here and just kind of focus on naming the compound because I'm trying to make sure I'm looking at the time and how many slides we have left. So I'm going to skip this part here. They're just showing you this is what the side groups look like. If they have 1 carbon, they're called methyl. If they have 2 carbons, ethyl, 3 carbons, propyl, 4 carbons, butyl. They retain the same prefixes we're going to be using for the longer chain. So that kind of makes it easier. 1, 2, 3, 4, 5. Pentyl. 6 is hexyl. Of course, you have nonyl. Oh, 7. Heptyl, octyl, nonyl, and then decyl or decyl, whatever. The idea here is the number of side groups have to be represented in the description of the side groups. Okay? So once again, this makes more sense as we are working it out. So this is the detailed steps, or I should say detailed components of the name. Organic molecules, oops, sorry. Organic molecules tend to have all of these components in the name. Okay, so I won't go over this right now because I feel like it's a good summary when we're done versus looking at it first. Okay, so number 1. We're going to go through how to name alkane using the IUPAC system. It says here, find the parent carbon chain and add the suffix. So this is the molecule that we're trying to name right now. You want to locate the carbons connected in series, like back to back to back to back. So I guess we're starting from here, right? So this carbon, we're counting as carbon 1, this is 2, this is 3, this is 4, this is 5, this is 6. You want to find the longest chain. So I'm going to show you variations, right? So I can highlight this. If I start from left going right, this is one possibility, okay? I could also start from the top. You want to be aware of that. I can start from the top and go left. This is not a possibility. That's not long. That's only 3 carbons. They said find the longest chain, but I want to make sure the chain I selected is the longest possible. Okay? I'll try one with pink. I start here and I go to the left. 1, 2, 3, 4, 5, 6. Oh, just like the first one. So I'll pick the first one because it has the longest chain possible, which would be from left to right. Okay, 1, 2, 3, 4, 5, 6. Since I have 6 carbons, I'm going to name it hex for 6 carbons. Notice all these carbons have single bonds. So hex stands for 6 carbons. A and E from the alkane family. Okay, so this is the last name you will write. Hexane. And as we are writing this name, we're building it from right to left. So we're kind of working backwards. So we're starting with the last name of the chemical, hexane. Then we're going to fill in stuff in front of the hexane. Okay? Okay, we got the longest chain. Not necessary. Good questions. We're starting from left to right because there's a lot of the side group is in the left. We tend to start from the side that's busy. Okay? This side on the left has a side group, so we prefer the side that has the side group, if that makes sense. As we're working on this in the other chapters, you see the same thing. So the side that's busy is where we start counting. 1, 2, 3, 4, 5, 6. Okay? Good questions. Okay. They're telling you the longest chain can come in different forms. So I'm going to skip this for right now, and I want to keep going on. Okay. Number 2, step 2, number the carbons in the parent chain to give the first substituent a lower number. Our goal when we're describing the location of CH3 is to give it the smallest number possible. So for that reason, we must number this from the left to right, carbon 1, 2, 3, 4, 5, 6. So when we're describing this, we say, oh, by the way, there is a CH3 group attached to carbon 2. You're like, oh, versus had we flipped it and numbered it from this, we'll say there's a CH3 group attached to carbon 5. So these were the rules made by the people who met. I wasn't even born then. They met together and they said these are the rules that we shall follow. They call it the IUPAC rules, and everybody else shall follow. Aye. And they signed a document, I think. I don't know. But anyway, okay. So we start from the busy side, the side that has a side group. Okay, so this is not right and this is right. 1, 2, 3, 4, 5, 6. Okay, so we're saying the side group is attached to carbon number 2. Okay. Now it says name and number the substituent. This is the side group. The side group. Okay. So remember, this right here is the parent chain. I like to mark the parent chain. So whatever element or whatever piece didn't make the cut for the parent chain, that will be the side group. Okay. So the parent chain is the one right here making this the side group. The side group only has one carbon. Do you see that? Right here. So by having one carbon, it's called meth, meaning one carbon. Ill. Meth ill means your side group has one carbon, but it's attached of all the carbons we have available. So let's see, when did they finally name it? When did they finally get to it? Are they just going around? Okay, they finally give the answer. Okay, so let me try before I get to what they're saying. So remember, the longest chain has 6 carbons. 1, 2, 3, 4, 5, 6. So for 6 carbons, we have the name hexane. The side group has 1 carbon, so it's called methyl. So I'm going to write here methyl. Okay. Longest chain, 6 carbons. Side group has, or side chain has 1 carbon. Okay. But what carbon is it connected to? Carbon number 2. So you say here 2. And if you have a number next to a letter, you have to have a dash. Okay. I know. These are the rules. So when you have a number next to a letter, there must be a dash sign. Okay, so 2-methyl. You can put these together, no space here, that's fine. You can space them out, that's fine. Either way is fine. I think they wrote them together, 2-methyl hexane. Okay. Do you have a question? Okay. And well, if you have a number next to a letter, there has to be a dash. What if you have 2 numbers? There has to be a comma. These are their rules. So let me see. Where do I write that? I'll write it somewhere here. A number next to another number is separated by a comma. I have to make sure I spell comma right. Is that how you spell comma? This is how we'll spell comma for right now. Right. So if there were two of them, we'll say like 1, 2 dash. Very systematic. So there are different groups of chemists, and these are the organic chemists that came together to make up these rules. Okay. So I wanted to make sure I explained it to the end before we kind of go into other avenues right here. So every carbon either belongs to the longest chain or the substituent group, but not both. Each substituent group needs its own number. So all those side groups have their own numbers. But what if you have more than one side group? If you have more than one side group, it has to be defined, or if they're more than one side group and they're identical, you have to use a prefix to indicate how many you have. This is where if you have two of them, they say di, tri, tetra, and so on. Okay. So with this class being an animated class, it doesn't feel like it, but it is. We will keep it simple when we're naming the compounds. Okay. So here's an example of it's similar to what we had before, but they brought in a second group. Okay. So once again, the longest chain has 1, 2, start naming from the busy end. 1, 2, 3, 4, 5, 6. So for this structure here, we still have hexane as our longest group. Our next word will be written to the left. We have a methyl group here with 1 carbon, another methyl group here with a second carbon. So this would be methyl. But don't we have two of them? Yeah, we do. So I'll say di. Okay, dimethyl. Okay, so dimethyl meaning on the longest chain, hexane, where the 6 carbons in series, we have methyl groups. Okay, how many? 2. The next question is, where are they located? Right? On the second carbon and on the third carbon. So you write on the second carbon and on the third carbon, dash, there is 2 methyl groups attached to the longest chain. So it's not just a name, it's a story. It's a description of the locations of these side groups. Okay? So 2,3 dash dimethylhexane. I know. You get a chance. I'm trying to go over this now because when we go over it in chapter 10, you follow the same trend with the other chapters. So I think the other chapters get slightly, I don't want to say easier, but they become familiar because it's the same as chapter 10, but applying to different scenarios. Okay, like you have double bonds there, triple bonds and stuff, but the nomenclature system is not that new. It's very similar to what we're doing in chapter 10. But chapter 10 is where you first encounter all of this stuff, and it's like, woo, overwhelming. But it does get better. Okay. And so here they're saying, well, what if there's more than one substituent? What if the side groups don't have the same name? What if you have ethyl and methyl? They tell you here, if there's more than one type of substituent, you want to alphabetize them. So somehow I feel like these guys, and I say guys because in the past, people who did science were mostly men, right? They're like kind of a little OCD. This group of chemists are a little OCD in how they want things done. Very specific, but then they're very lazy. They're lazy and very particular, right? So you gotta alphabetize them. Two numbers have to be separated by a comma, number and letter by a dash. If you have so many different side groups with different names, alphabetize them, make sure they're in the right order. Okay. I did talk about the separating numbers by comma and then separating numbers from letters by dashes, so we're good. I've already named this one here, right? And I already named this one here too. Okay, so let's see if we have, oh, they gave us this one here. Oh, snap. Okay. With this one here, I'll just work with them because we have our own to name down here, which we'll get to practice. Okay, let's see. For this one, longest chain. And then you get a chance to do the same thing over and over again. So as you're learning, you're practicing, right? You're practicing and you're learning at the same time. Okay, which end is more busy? Let's see. If I start from here, one, two, three, three, the third carbon is where stuff happens. If I start from the left, one, two, okay, so the left is more busy, right? So the way I picked out which side was busy, I figured out which carbon has the first side group. So I'm gonna number from here. One, two, three, four, five, six, seven, eight. So eight carbons, the longest group, the longest chain, and these are all single bonds. That's where we get the octane from. Octane. I know they have it written there. I'm going to do it from scratch. Okay, let's see. What are my side groups? I'm going to highlight my side groups using a different color, a brighter color. I have this one here called methyl. I have this one here also called methyl. I have two methyls. Then they gave me another one here in the middle called ethyl. Whew! They're combining all the rules. It's like we just barely learned them, and now it's like we have a huge remix. Okay, let's just focus and follow the rules. Since we have two side groups with two different names, I have a methyl. I'm going to write on this side first, right? I saw that one first. I have two methyls. So since there are two of them, one here and one there, I have to use the word di to indicate two. I have two methyls. Where are these located? Carbon 2 and carbon 6. So 2, comma 6 dash. So on carbon 2 and carbon 6, I have two methyl groups. That's what this means. Okay, I'm done with the methyl. What about the ethyl? I also have an ethyl. Okay, where's the ethyl attached? It's attached to carbon 5. So 5 dash. Remember, between a letter and a number, there has to be a dash. Now that I have my pieces together, well, set up on the side, I now have to put them in front of octane, but I have to put them alphabetically. So in this case here, let's see. E comes before M. Yeah, this is the tricky part. Ethyl comes before methyl. We're not looking at the die. So ethyl comes before methyl. For that reason, we'll write it as 5 dash ethyl. Okay, this is a letter. The next thing I'm going to write is a number, so I have to put a dash here. I know they're very, very particular. Comma 6 dash dimethyl. I know. Like, really? Yes, really. Okay, we're gonna practice our own without any guardrails or whatever. Oh, okay. I like these ones better. They give us a chance to kind of practice. So I'm gonna do some, not all, because I'm trying to make sure we get to the end of this. Yeah. So I'm gonna pick the harder ones. Like this one here is easy, so I'm gonna do this one here, and then this one here. Woof, and I guess that one. Okay. So for this first one, I need to draw it out because let me select the longest chain first. If I count from the left, this is one carbon, 2, 3. It doesn't look right. What if I count from the top? 1, 2, 3, 4, 5, 6. Okay, that's 6. Okay, let me try it differently. One, oops, wrong thing. 1, 2, 3, 4, 5, 6. I think that's my longest combination, right? So I'm going to do it that way. So here, this will be my longest chain, okay? When it comes to numbering, I'm going to try to number. I'll number it from here. 1, 2, 3, 4, 5, 6. If I number it that way, then the side carbon is on carbon 3. But if I number it the opposite way, 1, 2, 3, 4, 5, 6, that's a lot better. Okay, let me number the opposite way because you want to run into the side group faster. So I'll number it as 1, 2, 3, 4, 5, 6. This side group is attached to carbon 2. You see that? So we get to it faster. Okay, my longest chain has 6 carbons. It goes like this, right? So that will be hexane, 6 carbons. Then I have two side groups. one here, and one here. This side group is on carbon 2. It's called methyl because it's only one carbon. This is also called methyl. So they're both called methyl. Let me just combine the names. Two methyls are dimethyl. The first one I run into is on carbon 2. So 2, comma. The second one's on carbon 4. 4 dash. Oh, okay. So I'm going to move this over here. 2, comma, 4 dash dimethyl hexane. How are we doing, guys? It takes a little working on this. Okay. Oh, that's a thumbs up. Okay. It takes a little working on this to kind of get used to it, but you're going in the order. Last name first, then middle name, then first name, right? Kind of like from right to left. This one here I have to decode first. I need to write it out so I can see what it looks like. Okay. I'm going to draw this part and this part first because these parts look complicated. So I have a carbon here and a carbon here. Then to this carbon, there are two CH3s. CH3, CH3. Then we have a hydrogen. Oh, okay. I think I'm getting it now. To that carbon, same thing. CH3, CH3. Then I have this hydrogen. Okay. Now I'm trying to name it. I have to find the longest chain. I start with a carbon, right? I'm going to start up here. This carbon, this carbon, this carbon, and this carbon. Okay? So my longest chain I see here has 4 carbons. 1, 2, 3, 4. If it has 4 carbons, can I write on the right? Oh, okay. Butane, because it has 4 carbons. Okay. What are my side groups that not make the longest chain? This is one of my side groups. This is one of my side groups. Oh, I forgot to number. Bad, bad. Okay. 1, 2, 3. Yes, we're always following the pattern. Exactly. This whole class, patterns, patterns, patterns. Right. 1, 2, 3, 4. Right. So on carbon, oh, I have 2 methyl. This is called methyl, right? And this is called methyl. And there's 2 of them. So when I consolidate the name, I get dimethyl. What position are they on though? Carbon 2 and comma 3 dash, right? So I can put this over here. 2 comma 3 dash dimethyl, right? These are not easy ones, and I picked these ones to make sure that we can work, and they're working hard. We're working hard, but you guys won't always have to do stuff that's that difficult. I mean, some of it will be, some of it won't, but yeah, they always follow this pattern, correct words. It's a pattern, right? You see me do the same thing over and over again. It's been a while since I've taught this class, so even I'm having to relearn the pattern. I'm like, what's the pattern again? And I don't have the best of habits, so that's a challenge. Okay, so this one here is a lot easier to tell, I think, that you get to the side chain by going from the right, right? So 1, 2, 3, 4, 5, 6, 7, 8. I think that's my longest chain, right? With 8 carbons. So I'm going to write the name here, octane. 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then I have 2 small side groups, 2 tiny ones. What carbon is this on? 1, 2, 3. Okay. So I see 2 methyls, right? These 2. One is on carbon 3, then the next one's on carbon 4. So 3, comma 4 dash. Okay. What about this one here? This next one has got, I need a space. It has 2 carbons, so it's called ethyl. And it's on carbon 4, so 4 dash ethyl. Okay, well, like we just saw, right? The E comes before M, so you put the 4 dash ethyl first. And then since this is going to be converted into a number, you have to put a dash, 3, comma, 4 dash. Oh, I wrote too big. Hold on a second. I can rewrite that. Dimethyl Octane. Man, that was a beast, guys. That was a beast. But we are following the pattern, right? We're blindly following the pattern. As I said, doing the reverse is a lot easier. So let me pick some interesting ones, some fun ones. Whoa, what in the? Okay. You don't have to go through all of these. Let me pick some interesting ones. That one, it looks weird. This one looks weird. And that one looks weird. Okay. So I'm going to work on the weird ones for this one here. 3-ethyl 4-methyl hexane. Okay, so when I'm drawing my own structure, I'm starting from the right. Okay, hexane, 6 carbons. 1, 2, 3, 4, 5, 6. Okay, and then on carbon, oh, 1, 2, 3, 4, 5, 6. Okay, this is done. On carbon number 4, there should be a methyl. This is 1 carbon. So 1, 2, 3, 4, there should be a methyl. This is done. On carbon number 3, there should be an ethyl. On carbon number 3, I should have an ethyl, 2 carbons. Yep, done. Now all I have to do is fill in my hydrogens, right? I have 1, 2, 3 here. 1, 2, left, 1, 2. There's a one little one over here. 1, 2, 3. I'm just filling in to make sure each carbon has got 4 bonds. There, 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 there. And that's my structure. As I said, I'm going to do the weird ones, the ones that looks a little wonky. Your assignments will not always be this weird. For the labs, I think the later labs, I'm picking the ones from the book. You know, the ones from the book you received. And so, yeah, this is the first one. I might need some more space. This second one here, 6-butyl-3-methyl-decane. Wow, decane is, let me see if I can add some space. I may need some more space to make the pictures look better. Okay. Copy. Oh, no, 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 what am I doing? No, let's just copy. Just copy. Okay, sorry. Okay, put over here. So now I'm doing 6-butyl right here. So 6-butyl, this is 4 carbons, -3-methyl, this is 1 carbon. Decane, seems like forever. Decane is 10 carbons, right? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. 10. I put the 10th one here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I was too close to the right. Okay, so I have my carbons. Let me put in my bonds here. I'll put 4 bonds around each one. You know what? I'm not going to fill in the hydrogens. I just leave the bonds as is because it takes up time. But you get the idea. Okay, these are my 10 carbons. So I'm done with that part. It says there's a methyl group on carbon 3. So 1, 2, 3. I put a C here for the methyl group. Also has 4 bonds. That's done. And then go to carbon 6 and there's a butyl. This is 4, 5, 6. I'll write it down here. 1, 2, 3, 4. And then you fill in the bonds and put in the hydrogens. Okay? So I'm not going to fill on the hydrogens because that takes up time, but this will be this structure right here. My last one, 3-ethyl, let me just copy that and then paste it down here. They take up a lot of space, these structures. That's okay. This is not real paper, so I think I'm fine. Okay, now I'm going to do no name. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Draw in all your bonds here. Up, down, up, down. Do I have my bonds? Oh, okay. Up, down, up, down, up, down, up, down, up, down. I'm done with that part. 5-propyl. Prop is 3 carbons. F is 2 carbons, so 5. 1, 2, 3, 4, 5. On carbon 5, I have 3 side carbons. This is done. bonds here, right? And then on carbon 3, 1, 2, 3, I have 2 carbons, 1, 2. Once I fill in my hydrogens in there, I'm done, right? I won't fill it in because it takes up time, but that's my structure. So hopefully you can see how we go forward and we go backward. Let me see. How am I doing on this? Oh, this is an example of the systematic name. Imagine that complex name, right? Somebody got paid to come up with this name. This is the systematic name for ibuprofen. Systematic name. So essentially, most drugs have 3 names. Systematic names, generic names like ibuprofen, trade names like Motrin or Advil. So just FYI. We talked about all those acyclic structures. We're done with those. So the remainder is now the cyclic ones. The easiest way to draw the cyclic ones is skeletal structures. That's where skeletal structures are really your friend here. See this cyclopropane? Just draw this with the 3 carbons. You know the hydrogens are implied over here. Here you have the 4 carbons. The hydrogens are implied. Because it's skeletal, remember in skeletal structures we leave out the carbons and the hydrogens. So I'm going to say here, in skeletal structures, leave out carbon and hydrogens. They're implied. So every corner here is a carbon and the relevant number of hydrogens. Okay? So they show you that this is a cyclopentane, cyclohexane. And then finally, we're doing the naming. And I'm thinking this is the last part, last but one part at least. With naming the compound, the cyclic compound, just like before, you see how it begins to relate to what we just did? There's going to be 4 parts to the name. The suffix tells you what functional group you're dealing with. For example, this is an alkane, right? The parent name tells you how many carbons are in that ring. So this time, when you're dealing with cyclohexane, the parent is the ring. So you're counting how many little edges do you have in the ring or little corners do you have in that ring. You have to include the term cycle so the person on the other end reading reading the name knows you're referring to a ring. When you see cyclo, you're like, oh, cyclo. It's a ring structure. Okay. The prefix, these are the regular prefix, the methyl, the ethyl, the propyl, all those groups. You want to state where they're located. Okay, that's it for the naming. So let's get right into this. Oh, they threw us right in for a loop. Okay, that's okay. Find the parent cycloalkane. So we're going to start, we're naming the cyclic compound, right? So find the parent. This right here is your ring. The ring has how many carbons? 1, 2, 3, 4, 5, 6. Okay, so we have 6 carbons. So you're going to say here, alkane. Oh, sorry. No, alkane is a generic name. Hexane for 6 carbons, but it's cyclic, so cyclohexane. You want to add the cyclo prefix to communicate that it's cyclic. Cyclohexane. Okay, so now these are going to be your side groups. Of course, remember this is methyl, right? We recognize that. Methyl. And this with 2 carbons, ethyl. Yeah. The more you work on this by chapter, let's see, this is chapter 10. By chapter 12, these are very familiar because they'll be the same side groups all the time, all the way to the end. Then it says number, name and number the substituents. No number is needed for the cycloalkane with a single substituent. So here we're kind of detouring, right? If you just have one side group to the cycloalkane, you don't have to number it because everybody knows that will be the first carbon. It's implied, it's understood. So you won't write 1 methyl cyclohexane because people will be like, of course it's 1. What else can that carbon be labeled? That will be your first carbon. Because it's understood, you leave out the number. Okay? Once again, over here, you only have 1, 2, 3, 4. 1 butyl, right? You don't have to write 1 because everybody knows that's the first carbon. You want to assign carbon number 1 to the one that has the attached side group. Okay? But if you have more than one, it says when you for a ring where you have two or more substituents, begin numbering at one substituent. Okay, that makes sense. Well, which one do we use though? Then proceed around the ring to give the second substituent the low number. Here's the bottom line. They want low numbers on side groups. Okay? So we get that. They said this already. They want the side groups to be assigned the low number on the carbon. Well, what if you have two different substituents? If you have two different substituents, number the ring to get to assign the lower number to the substituent alphabetically. Man, they like that lower number and alphabet thing going on. So what they're saying here is if you have an ethyl and a methyl, make the ethyl number one, and then the methyl will be the other number. Okay, because they want the lower number to go with the letter that appears first in the alphabet. They had to come up with something that they agreed on. This is what they came up with, so we just follow them blindly. So back to ours. Now that we know this is going on, I can now say I'll make this number one, right? I'm not gonna go what is this? Clockwise. I'm not going to number this clockwise because it will give methyl a very large number. I'll number this counterclockwise because they want the numbers to be small. So I'll say 1, 2, 3, 4, 5, 6. So my cyclical part is cyclohexane. And then on carbon 1, I have my ethyl. So I'm going to say here 1 dash ethyl. On carbon 3, I have my methyl. Okay? So let's see how they combine them together. Oh, man, they mess around a lot. They detour because I was like, wait, what? No, this scenario here, the two side groups are the same. Okay, the two side groups are the same. So they just numbered one of them 1 and the other one 3. So here's 1, 3 dimethyl cyclohexane. What about the one we're working on? Oh, finally, back to this. So finally, once we had that, you then write the one that's E first. So 1 ethyl dash 3 dash methyl cyclohexane. Okay, remember the lower number goes with the side group whose name starts with a letter that appears first in the alphabet. I'm serious. I mean, when I was learning this, I was like, they should have invited me to that meeting because I'd be like, listen, man, make this simple. This is the rules they chose, and this is how they name it. It's systematic, IUPAC system, and all of us follow that system in naming these compounds. Okay. Oh, after all that fun stuff, let's go ahead and name these. Okay, so I'll pick two because I know you guys are getting fatigued, but we're close to the end. Look at the slides. We're close to the end. Okay, since it's a little tricky, I'll name this one here. This is one group, right? Methyl. Because it's one group, you don't have to say one, it's implied. And there's 1, 2, 3, 4 carbons. So the longest group is cyclo, right? Because it's cyclic, butane. Cyclobutane. Then we have the methyl group, so I'm going to put here in methyl. You don't have to write one because everybody knows that's going to be one. So methyl cyclobutane. Okay. Now in this case here, okay, here's the rule, okay? I was gonna skip over some of these, but I realized now I need to go over this. In this case here, we have two methyls attached to the same carbon. Two methyls. Okay, 1, 2, 3, 4, 5, 6. So 6 is gonna be cyclohexane. Cyclo because it's cyclic, right? So I named the last name. Now I have two side groups, both called methyl. So I know I'm going to be combining these, right? Methyl. I'm going to be combining them to get dimethyl, but I have to describe where they're located. So because we have two groups on the same carbon, I have to put the number so the person reading this gets the same picture. So here I'm going to write 1, 1 dash, okay? So 1, 1 dash dimethyl cyclohexane. If I only had one, there would be no need to say one methyl cyclohexane. But since I have two methyls, I have to say they are both attached to the same carbon. So 1,1 dash dimethyl cyclohexane, right? It's a mouthful. Okay, let's see this one here. Ooh, I have to name these first. This is two carbons, ethyl. One, two, three. Three carbons, propyl. When you're numbering, you want a number, so the one that has the letter that comes first in the alphabet gets a lower number. So 1, 2, 3, 4, 5. Okay, so we have 5 carbons. 5 carbons is what? Cyclopentane. Okay, and then on carbon 1, I have my ethyl. So I'm going to say here, carbon 1, I have my ethyl group. On carbon 3, I have my propyl group. Now I have to combine them. So 1 dash ethyl dash 3 dash propyl. Following the rules, right? Okay, I'm going to squeeze this together. I'm going to squeeze them together. There. There. 1 dash ethyl dash 3 dash propyl cyclopentane. Following the pattern, right? This one should be a lot easier. Yeah, we've done something like this. So I'll skip over that part. What about these? We can do this one here, right? Let's start with the first one. Cyclopentane. I'll draw it like a house. There. Propyl. So anywhere. Propyl is 3 carbons, right? CH3, CH2, CH2, CH3. That's the first one. I need space for the rest of these because these molecules get really large. Okay. Second one, this. Okay. The second one says 1,2-dimethylcyclobutane. Starting with this last one, cyclobutane. Butane is a box. 4 carbons, right? Bute. 4 carbons. 1, 2. On carbon 1 and 2, I have 2 methyl groups, 1 carbon each. So I put here CH3, CH3. I could literally just draw it like this, and this will work. I don't know, like that. That will work. Pure skeletal structure, right? For this one here, if I wanted to make it pure skeletal, I could make it like this. And then 1, 2, 3. 1, 2, 3. Yeah, I could do it that way and that will work. Okay. Let me do this third one here. That. I'm working these out because I recognize they are a little bit challenging. So propane 3, right? Propane 3 carbons. That would be a triangle. And then I have 1, 1, 2 trimethyl. So let's make this carbon 1. This is 2. This is 3. I have two methyl groups on carbon 1 and then 1 on carbon 2. This reminds me of a TP or something. I don't know. This is a molecule in skeletal structure, right? If I draw it out this way, it's like CH3, CH3, CH3. You have 2 on carbon 1 on the same carbon, and then another one on carbon 2. Carbon 2 can be in the right or the left. Either way works. Okay? And then let's see, this last one here. Same pattern. Okay. Starting from the right. Cyclohexane. Okay, so hexane like that. 1,2-dimethyl. Let's make this 1 and this 2. This is 3, 4, 5, 6. So 1, 2-dimethyl. I'm done with this part here. 4-ethyl. 1, 2, 3, 4. 4-ethyl. CH2, CH3. Okay, so the ethyl, the one that has 2 carbons, this is 1 carbon, is in the 4th carbon. Okay, So hopefully you're seeing what I'm doing. Okay, we're close to the end, close to the end. So right here, physical properties. What we saw before in the previous lab, we're seeing here. Because alkanes contain only nonpolar bonds, CC and CH, alkanes have London dispersion force only as their intermolecular force. So they exhibit only weak intermolecular forces. For that reason, they have very low melting point, very low boiling point. They tend to be gases. So we're told smaller alkanes are gases at room temperature. Larger ones, due to their size, become liquids. And then alkanes are not soluble in water, because if a compound is to be soluble in water, I'll say here, to be soluble in water, the compound has to be, it has to be polar, or have hydrogen, or I should say here, or have hydrogen bonding ability. Alkane is nonpolar. It's like oil. So when I think alkane, I'm thinking oil. Oil will not mix with water because it's nonpolar. It will sit on top of water, but it won't mix with water. So we're told here alkanes are less dense. Once again, I'm thinking oil, right? Than water, meaning that it will float on the surface of water. Okay, so what if you're comparing one alkane to the other? The alkane on the right, these all three have London dispersion force, London dispersion force, London dispersion force only. Why? They are all non-polar, and non-polar compounds have London dispersion force as their only force of attraction. This will have the highest boiling point, right? Because it has the greater surface area and it has a greater mass too. Don't forget that greater mass. You got more elements in there, you got more electrons in there, so you have a greater surface area, greater boiling point. Okay? Okay, let's see. We're very close to the end. We're doing so. Answer the following questions about pentane and decane. Okay. Which compound has a what you have this, the one with 10 carbons, 5 carbons. Which boiling point? The one with the least carbons. It's going to be C10H22. Okay? That one. Because there's more elements in there, so it's going to take a lot more to boil it. Which compound has the lowest boiling point? The one with the least carbon, C5H12. Which compound has the highest melting point? Also the most carbon, C10H22. Which compound has the lowest melting point? 5H20, H12. Okay, so the most melting point and the most boiling point has the most carbons. Okay, most melting point and boiling point has most carbons. And this will help you, this part here, because I recognize this from your lab, will help you complete the lab just in case you haven't finished it already. Finally, the environment. So we're told here, no functional group, there are few reactions. For that, they burn. Combustion is the only means undergo. Okay, will when it reacts with oxygen, give you carbon dioxide water. So it's here, organic compounds, most organic compounds burn in oxygen to give carbon dioxide and water. I'll say here most, but alkanes for sure burn in oxygen, like fuel, right? To give you carbon dioxide and water. So when you're making a barbecue, you use that lighter fluid. The lighter fluid is most likely an alkane. So oh my goodness, they give you something so complicated. Bottom line here, as complicated as this alkane is, in the presence of oxygen, it gives you carbon dioxide, many carbon dioxide, okay? And this is the one that has the whole greenhouse effect. It's not good for the environment. and then it gives you water and energy, lots of energy. So in my on-campus class, when I used to teach this class on campus, I'll ask my students, have you had a chance to burn something? And they're like, no, it's illegal. I'm like, what? Where I come from, we burn stuff every Tuesday. Like it's like just another day, burning, burning, bonfire. You can burn whenever, whenever it suits you. You see random unattained to or unattended fires just here or there, you know? It's like we have no regulation. That's a bad thing, right? Because you have a lot of random fires. But you have a lot of heat as you're burning something, okay? So, yeah, the biggest thing you want to remember here is whether it's complex like what we have here, the high octane component of gasoline, or whether it's simple like we have here, alkanes burn in oxygen to produce carbon dioxide and water. Now, in this case here, we're told if there is not enough oxygen, we have something called incomplete combustion. Incomplete combustion is where you don't have enough oxygen, so instead of making carbon dioxide, you get carbon monoxide. Okay? Sadly, what happened in, was it January of this year? A lot of things have happened this year. I don't know what time. Before spring break, remember when we had the freeze over the ice? And I don't know if y'all are watching the news, but there was a lady who, an older lady who stayed in her car with her, either her daughter or her granddaughter. She was trying to keep warm. So she got in her car, turned on the car, but she had the garage door down. Now you know the car has gasoline, right? So the gasoline from the car will essentially be the alkane here. And by her closing the garage door, she limited the amount of oxygen in the garage. Had she left the garage door up, she would have had unlimited oxygen, and the gasoline would have burned off and should have had this equation instead, the regular combustion reaction. But she closed the garage door, and so the oxygen burned off until you had regular oxygen, and she unintentionally then poisoned herself and the little girl because when the oxygen ran out, it started to make carbon monoxide, and they inhaled it and they sadly passed away. The next morning, they found them in the car, passed away. It was very sad, you know? So if you don't have enough oxygen, you have this reaction instead. Anyway, yeah, so here they're asking you what are the products formed when this compound here, natural gas, undergoes combustion. You will write the formula down like this, CH3 plus oxygen. This is when you have a lot of oxygen, right? To give you carbon dioxide and water. But what if you have incomplete combustion? That's when you don't have enough oxygen for whatever reason. This gives you carbon monoxide and water. I know you're tired. I know. I feel tired and I'm the teacher. This has been a lot, but the good thing is you can go ahead and rest and then you watch this when you're rested, right? But I'm done. I'm not even going to balance this equation. Just know that you get carbon dioxide and water. Okay? Do you guys have any questions? And okay. So for okay, you're welcome. For this to be even more helpful, when you're rested, because by now I can imagine you're saturated, right? Like that carbon with the hydrogens. Let me not get there. Anyway, take a break, and then when you look at your lab work, you will see the relation, the correlation between what we're doing here and the lab work, and of course your homework. Okay. Tomorrow I'm going out with some friends in the evening. So what I'm gonna do is I'm gonna try to do the recording earlier in the day. If you guys can join, I'll let you guys know when I can do it. I'll let you know earlier. Hopefully my internet will be good. I hope it's good tomorrow. Please, internet. And then we can go ahead and meet. And then if you can't meet with me, that's fine. I'll just do a solo run and get the recording and post it for you guys. Okay? Because chapter 11 I think is sort of like the length of this chapter right here, so I will need to break it up in a couple of days. Okay, other than that, this is all I have. So okay, well, you guys have a nice evening.